Howdy, in this video I'm going to be going through the GUI and the general flow of the LabVIEW code that's happening with the Intronics packet. As you can see here in the front panel, there's several things we have noticed here. First off on the left, this is just some general information. The packet type is listed right here, along with your receive array. This is just what you receive as your initial packet. To the far left here is the decimal numbers and hexadecimal numbers for all of the sensors, IDs. That's not really changeable of any way. This is just more for information's sake. Right here is the controllable aspects. On the top we have the save file. The important thing to note here is that it does have to end in .tdms. That's the file type that the LabVIEW saves to. And there's an example always written up here. But you simply just have to change this to whichever location that you want to save to. This next box is just some general information. This is the number of writes being sent and the acknowledgement received. This number should always be a 16. After that is the total loop count that you're on and whichever current node you're on. Important thing to remember here is it does start from 0 and then goes up, as is binary starts at 0. This is the resource name. You're going to have to change this. There should only be one available if you only have the XB module in via USB to your computer. But sometimes this does change based on the computer. And this start button here, Boolean start, is just naturally always on. And this is the total number of loops that you would like the program to run through. Starting again, this is the read count. Now this is 19 based off the Intronics packet. If you want to add more bytes or less bytes, you can always change this number and to the appropriate number of bytes in your total string package. This is the milliseconds to wait in between nodes. You notice I have it here at 0. That's the fastest it can go. But you can also take this number and make it 1 second. Remember that it is milliseconds. Or you can make it 10 seconds. To the right of that is the number of nodes. This is the total number of nodes that you'll have. 1 being the lowest, and 3 being what I'm showing here on the right. If you want to add more, I'll be showing that in a different video of how to add more nodes. And on the bottom here, we have the count number. This is the count that's revving up inside the write, and the total number of times before it'll move on and pass that node. Below that is just the return number of bytes that you receive in the packet array. And finally, this is your actual write to the nodes. Here's where you write the node ID that you would want to get, and you can put them in any order. And now moving on to the write. Here we have a few buttons just to tell which node is selected, and if the node's transmitting at a given time, along with a timestamp below it. This timestamp tells you the last time that you received a data packet from them. Here we have the ambient temperature and board temperature. Both of these are able to switch to Celsius, but they only update whenever the node updates. This motion is just the motion detector, along with the humidity and the light readings. And then finally the 3-axis accelerometer, which shows the 3 X, Y, Z axes. And this is donated by blue, yellow, and red. Alright, now moving on to the block diagram. Starting at the far left. Here we just have some initializing variables, as well as resetting the waveform charts right here. So into the first loop, which is noted by the initialize loop. This is just where a good number of things are initialized. The loop count, for instance, and the total number of loops, thereby stopping the program as a whole. as well as resetting the current node back to 0 for the next loop. So here we have the outermost start case, and inside that is the total data loop. Now this loop will reset only whenever the current node is equaled to the total number of nodes. And then inside that while loop we have our first sequence. This is our write read sequence. It's an engulfing total amount. So to the left, and then now once again inside that, this is our write and acknowledgement loop. So here in the first sequence we have our serial settings being written to the USB dongle, and we want to immediately flush the transmit buffer, and from there send our current node ID and write that to the USB. And we'll go into this as well as any other sub-VIs in a different video. So once this is written, it sends it to the buffer and is written from the XB module. Now this timeout is set here to be 100 milliseconds, and that's the total maximum wait time that our read function right here will wait for an acknowledgement from the node. If it receives it, then it will cause this Boolean high and stop the program. Otherwise it will repeat up to a maximum of 30 times, and then thereby give a true and pass the data along, but this time being a false still on this Boolean line. And that false will trigger the case structure of the total read packet to be false and simply ignore and move on to the next node. Really quickly, I will show the false statement. As you can see here. And this simply takes the current node and adds 1 and then compares to see if it's ended the loop. Now back to the true statement. If it did receive an acknowledgement of 16, it goes into this case structure and starts off with the sequence of reading. And in the first sequence we have the read loop. So inside here we have our timeout for our string, as well as a break length. So this break length, as you saw earlier, was the read count. It's set to 19 bytes. That's why you have to change it if you increase your total packet size, because it will break the packet early. Now then, once it's reached the break length, it'll take the data that it has recovered and then put it into the read, and this will read the serial USB connection and then take that data that's in a string format, turn it into an array format, and here's the receive array that we saw earlier, and this will decluster the array, or it'll actually cluster the array, and then we unbound that cluster into all of our packets, our data bytes. From here, as you can see, all of the bytes have a certain name to them, and as well as a stop condition. This stop condition just checks to see if the first byte was the start byte and the last byte was the stop byte of 15. This area here is simply an error check for offline mode. Now then, a few things to note here. We do check for the 253 of the start and the node ID. This node ID determines which case will update, and that will be shown in a second here. And here we have all of the different data and type bytes. Now then, if this gives the wrong packet, this stop condition won't be met, and it'll move on to flush the receive buffer and then restart the loop. Once it restarts the loop, this will actually be 0, entirety of zeros. So the break length will break at a complete 0 byte, and the string will be consistent of 19 bytes of 0. This will force all of the data here to be 0 if an incorrect byte packet was received, and we'll force the node ID to be 0 as well. And then this stop condition, as the loop enters one total iteration, will stop the loop. And from there, the node ID will be 0, forcing the default case of nothing to happen. Now then, if a node ID is registered, we'll go with 1. Then the LED will turn on, as well as the timestamp provided. And the data previously acquired here will now be taken into several steps of how to be displayed on the front panel as well as saved. Humidity as well as the motion are simply just taken straight in with their numbers. Temperature, both temperatures have a separate case statement if they were on the Celsius trigger. And here in the light readings, we have two different statements to increase the total number of the total range that we have on our light sensor. And there is a -1 and a -81 here, simply to negate 0, because 0 does not transmit over the XB connections well. It gives bad data packets a lot. So we simply add 1 and then subtract it here. And moving on, here's the accelerometer data that we receive. This once again is multiplied by 10 on the other side and added 8 to eliminate any zeros once again, or negative numbers for this matter, and then can be redistributed as negative numbers here, and then is saved to the accelerometer graph. Once this process is complete, we can now save the data that was collected, and once again we'll go into this sub-VI later. Now that the saving and displaying is finished, this is the wait in between nodes if you choose so to use it. And the final bit, similar to the backside, just refers to the stop byte as producing a +1 to the node and flush the receive buffer. And if the nodes match, the loop will stop. And if this condition wasn't met and a 0 was read in the default, it will simply not add 1 to the node ID and reset the whole loop with the same node ID to receive another packet from that node. And this simply turns off the LEDs on the front panel. So for the next video, I will be going into several of the sub-VIs to show you how those work.